Hey guys, it's Professor Dave. Let's learn about nuclear reactions.
He knows a lot about the science stuff. Professor Dave explains.
The electromagnetic force is responsible for the entirety of chemical phenomena. That positively charged protons and negatively charged electrons are attracted to one another is the reason that atoms form, the reason that chemical bonds and therefore molecules form, the reason that those chemical bonds have differing polarities, which lead to differing reactivities, as well as a method for enzyme recognition of substrate and DNA base pairing, which leads to life itself. But there are three other fundamental forces in the universe. The four forces are as follows. There's gravity, which is the weakest, but it operates on astronomical distances. So when you're looking at planets and stars and galaxies, this is the only force that matters. Electromagnetism, as we mentioned, is what makes chemistry happen, and it operates on the scale of atoms and molecules. But the other two forces operate on a scale even smaller than that, the scale of the atomic nucleus. These are called the strong nuclear force and the weak nuclear force. The strong nuclear force is what keeps the nucleus together, preventing positively charged protons from pushing each other away and splitting up the nucleus. And the weak nuclear force is what facilitates nuclear decay. These are instances in which the nucleus of an atom changes in some way. They are called nuclear processes, and though they are more in the realm of physics, they are important for chemistry because they often cause transmutation of elements. That's when an atom will change from one element to another. So we need to know a bit about them. To reiterate, in a chemical reaction, only the valence electrons of atoms are rearranging when chemical bonds break and form. The identity of each individual atom remains unchanged. In a nuclear reaction, changes occur to the fundamental particles in the nucleus of an individual atom, which means it will change from one element to another. These reactions are some kind of nuclear decay, where something in the nucleus disintegrates, giving off some form of radiation in the process. Radioactivity was first discovered by Henry Becquerel in 1896. He noticed that photographic plates had bright spots when they were exposed to uranium minerals. This radiation was found to be composed of three types when exposed to a magnetic field, since they were deflected in different manners. At the time, we didn't know about the subatomic particles the radiation was comprised of, so we just named them with Greek letters, and discovered their identities later. An alpha particle is essentially a helium nucleus, 2 protons and 2 neutrons. Emitting an alpha particle will result in transmutation, as seen here. A beta particle is an electron. A positron is the antimatter particle of the electron, which has the same mass as the electron but a positive charge. And a gamma particle is a photon of light. This is the same as the electromagnetic radiation from the Bohr model, just no longer associated with the transition of an electron. Let's quickly learn the ways that we can notate these particles so that we can write nuclear reactions. Remember that when we write nuclide symbols, the lower number is atomic number, or number of protons, and the upper number is atomic mass, or the protons plus neutrons. So a proton and neutron will be signified this way with a P and an N, each with mass 1, but only the proton has atomic number 1. An alpha particle can be represented as helium or with the alpha symbol. An electron can be either an E or a beta symbol, and the atomic number will be -1, while the mass, though technically not 0, is negligible, so we call it 0. A positron will be the same but with a +1 here. And a photon will be gamma, both numbers 0, as it legitimately has 0 mass. So if we want to describe the emission of, say, an alpha particle, we would write it this way. Show the first particle, the arrow signifies a reaction, and then show the alpha particle. To figure out the resulting nucleus after emission, we just do some arithmetic, because the atomic numbers and mass numbers have to add up to the same number on both sides, kind of like how we need the same number of atoms on both sides of a chemical equation. If the atomic number is 86 on the left and there's a 2 on the right, we need 84 for it to work out. Again, with mass, 222 on the left, 4 on the right, we need the other particle to be 218. Any atom with 84 protons is polonium, so the resulting nuclide symbol must be this. Again, the numbers on each side of the arrow add up to the same thing. Now that we are aware of these processes, why do they occur? It's always due to some instability in the nucleus. One reason might be that the nucleus is just too large. You see, the strong nuclear force, which is mediated by particles called mesons, is very strong, and it keeps the protons and neutrons fused together with 100 times greater force than the electromagnetic repulsion that wants to push the protons apart. But the strong nuclear force drops off with distance more quickly than the electromagnetic. So, if the nucleus gets too big, all of a sudden the strong nuclear force is too weak over the diameter of the nucleus to keep it all together, and the protons will push apart. So for atoms larger than bismuth, the nucleus is just too big to be stable. Nuclei like these will often rapidly emit an alpha particle to try to get a little smaller and a little more stable. But even if the nucleus isn't too large, it may have a number of protons or neutrons that isn't ideal. The shell model of the nucleus describes nucleons as existing in levels or shells, kind of the way electrons do. As it happens, there are so-called magic numbers for each nucleon that correspond to a special type of stability, kind of like a full valence shell of electrons. These are the magic numbers. In addition, most stable isotopes of a given element have even numbers of both protons and neutrons, and most of the rest have at least one of them in even numbers. And lastly, an atom will tend to want a certain neutron to proton ratio in the nucleus. For smaller atoms, this is roughly 1:1, which is represented by this line. But for larger atoms, this becomes closer to 1.5:1, so more neutrons than protons. This ratio gives a nucleus balance, so if an atom veers too much in one way or the other, nuclear decay will allow it to adjust the ratio. So as we said, if a nucleus is too large, it will emit an alpha particle, or it can undergo spontaneous fission, where it breaks into multiple lighter nuclei and usually a few neutrons. In beta emission, the reason an electron is emitted is because a neutron spontaneously transforms into a proton. Remember before how we said that protons and neutrons both weigh 1 atomic mass unit, even though technically the neutron is slightly heavier? Well, it is heavier by exactly the mass of the electron, which is why a neutron is neutral. It's a proton and an electron combined. So when the neutron becomes a proton, it will emit an electron in the process. A nucleus would do this if the neutron to proton ratio was too high, meaning too many neutrons, as this would adjust that ratio favorably. Positron emission is just the opposite, when a proton becomes a neutron. This will emit a positron because this is the process that is the opposite of beta emission, and a positron is the opposite of an electron. This would happen if the neutron to proton ratio was too low, meaning too many protons. With both of these types of decay, there is also a tiny particle called a neutrino that is emitted. In beta emission, it's an antineutrino, and with positron emission, it's a regular neutrino. More on that in particle physics. Another process that can occur is electron capture. This is similar to positron emission in that a proton becomes a neutron, but it does so by absorbing an electron rather than emitting a positron. Once again, a proton plus an electron makes a neutron. The electron in question will tend to come from one of the inner orbitals of the atom, and the electron will be a reactant since it is absorbed by the proton to give a new particle. And lastly, if a nucleus is in an excited state, it can emit a high-energy gamma photon. In this process, there is no transmutation because we don't change around any protons or neutrons. So we can predict what kind of nuclear decay a nucleus might undergo by looking at its condition. Is it too large? What's the proton to neutron ratio? Each decay process has its typical cause. Too many protons, positron emission or electron capture. Too many neutrons, beta emission. Too big, alpha emission or spontaneous fission. Excited, gamma emission. An unstable atom can undergo a radioactive decay series that over multiple emissions generates a stable nucleus, like uranium-238, which eventually becomes lead-206. So now we know what radiation is. It's unstable nuclei emitting high-energy particles. The reason this is bad for biological organisms is that these high-energy particles can tear through our cells, and if one strikes a DNA molecule, it can potentially change the genetic code at that location, resulting in a potentially harmful mutation. Most elements have naturally occurring isotopes that do decay over time, even carbon, hydrogen, and oxygen. So there are radioactive nuclei decaying all over your body every second. Luckily, we have enzymes that repair DNA damage as it happens. But if we were to be in the presence of a highly radioactive substance that is emitting particles at a high frequency, this would do much more damage than our bodies can repair. So we have ways of detecting radiation like Geiger counters. We will often talk about radioactive material in terms of a half-life. This is the time it takes for a material to be depleted to half the original amount. After 2 half-lives, there would be 1/4 the original amount. After 3 half-lives, 1/8, etc. Half-life is given by the following formula, where K is a constant specific to the material. By learning about nuclear processes, we can harness the massive energy they contain. With nuclear processes, matter is converted directly into energy, as is given by Einstein's famous equation E = mc². Here, c is the speed of light, which is very big. So what this equation says is that matter is simply extremely dense energy, the densest form there is. We have harnessed this power already with atomic bombs, much to the dismay of mankind. These worked by bombarding unstable uranium nuclei with neutrons, which cause them to split, generating more neutrons, which collide with other uranium nuclei, causing a chain reaction that releases tremendous energy. An even more powerful process is nuclear fusion. This is where small nuclei combine to give larger ones, a process that involves a loss of mass, which is converted into even more energy than a fission reaction. Reactors that harness the power of fusion promise to solve all kinds of problems regarding renewable energy sources, and could be the key to the next step in societal advancement. Maybe you can aid in the advancement of this or other important technologies. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.